Battiloro. He's a postdoctoral research fellow at Harvard, the School of Public Health, and he's doing a lot of advanced machine learning techniques in environmental health. So let's welcome here, and the floor is all yours.
Thank you, Roberta, for having me. Nice seeing all of you. The title of the talk, as you see, is very generic. It's climate adaptation in the AI era, and the talk will be kind of high level. Is more a way of giving you my vision, our vision, and to keep you posted about something on the thing that we are doing. So this is more or less the outline. I will give you some motivation on why AI and climate adaptation can go in the same sentence. That I think is a fair question. And then I will provide you with what we believe is the key. That is, AI is for sure not always good. And on the other side, is not always bad for climate adaptation. So there must be a good way of being resilient to AI, resilient to its carbon footprint, resilient to the production of pollution. And on the other side, AI can be used for many things that are for climate resilience. So to perform climate adaptation and to inform climate adaptation strategies. So very, very quick introduction. We have two, when we talk about climate change, most of us implicitly refer to greenhouse gases, to CO2, that on long run will make our planet warmer and on the long run will kill us somehow. But there are also hazardous air pollutants, PM2.5, that actually have a very short and mid-term impact on our health. So at the end of the day, is it in the short, medium, or long term, the climate crisis is an health crisis, is equivalent, probably the biggest health crisis that we are having in our century and in the following, unfortunately. And these are some very quick numbers, but when we talk about AI, the carbon footprint of AI, the elephant in the room is the energy consumption that is needed for AI, and the electricity demand, especially related to data centers, and more in particular to AI data centers, boost a lot. And the consumption is anyway projected to double in the next couple of years. So things are not going to be better. The point is that, and this is the gap in the literature and in what practitioners do, in climate practitioners do, is that we have many good AI models that work for climate. So we have, for example, many good weather forecasting models, many good physics-based models that can give you accurate estimates of CO2, maybe PM2.5, maybe they can tell you how it's going to be the weather in the next 2 weeks very, very accurately. And then we have another disjoint branch of model that instead are focused on health. I think that probably all of you, at least once in your lifetime, had to do with large clinical models. So you have these big models that are very good for health tasks, Q&A, or maybe self-diagnosis, and all of this kind of stuff. So we have very good model for climate, we have very good model for health, but in reality, what we really need for climate adaptation is something that puts them together. And this is something that is not there yet, and that as I will tell you, we're trying to do. Because it's just a matter of terminology here, but there is a huge difference between what is meant to be climate mitigation and what is meant to be climate adaptation. Climate mitigation means that we want to make our planet cooler. We want the CO2 greenhouse emission to diminish in time. And this is so more of a long-term goal that is related to greenhouse gases. Climate adaptation is all the set of strategies on the short, medium, and long run that allows us to save lives, to evaluate, assess, and resolve eventually the impact of pollutants, of hazardous air pollutants on our health. So climate adaptation will not exist in most of its flavors without having an eye on health. This is our picture. It's what I was saying before. We need AI to inform better climate adaptation strategies, and we can leverage it. But also, we need to make sure that we do it in a sustainable way, and because the energy consumption is increasing, the greenhouse gases production is increasing, And also, as a byproduct of that, also the hazardous air pollutants are increasing because of AI. So, you know, I work on AI, I'm a computer scientist, but I'm not an AI enthusiast. Like, I'm not the guy that says we should solve everything with AI. It's not the truth, it's not magic. And most of the ways we are using AI in this historical moment is probably harmful for us. So we need to keep an eye on the whole picture, and the whole picture is that not only using AI, but also making sure that we are resilient to AI and all the damage that it can make. Let's start diving a little more. I will give you some example of what I mean for resilience to AI and what I mean for AI for resilience. And we will start from resilience to AI, and we will start by analyzing what is the energy consumption that is now attributable to data centers. And I will present you with one of the ideas that is already a preprint online of what we call health-informed or health-based power grid optimization. So how can we take climate adaptation directly into account when we optimize the grid? And then in AI for resilience, in the second part, I will tell you more about how can we fill the gap that I just talked about, so the fact that we have this joint health and climate model, and what could be a principal way of putting these things together, these two work together, and produce a climate adaptation foundation model. So these are some numbers of data centers. We are more here in the climate mitigation stage, but still it's very important. And these are from a recent preprint from our lab. As you can see, the numbers are crazy. Like data centers accounted for over 5% of the total US electricity consumption, and they generated an unreasonable amount of greenhouse gases that represents around the 3% of emission of the US in 2023. This is the climate mitigation side. This is probably what you usually hear more around you. You know data centers produce CO2, data centers are harmful, and so on and so forth. What you think about a little less, and this is not from our lab, but is another recent paper, is what is the health cost of AI? What does AI imply for climate adaptation? This is just a number from this paper. There are more. You have the refs here, but the health cost has been estimated to be 5.6 billion in 2023 of AI data centers. And this means that is equivalent to the 43% of their total electricity cost. So these two, both the electricity cost and the health costs are comparable, and at the end of the day are pretty bad, both of them. So you have here some more number. They give you the electricity cost. They give you also the mortality. Those are exactly number of life. The health cost here is an aggregated measures that is generally public health costs, so hospitalization, what does it mean for the infrastructure and health, and so on and so forth. So what we thought while looking at this is that, you know, one could start with the more radical solution that is, okay, I want to control where data centers are placed. And that's, you know, a possible solution. It's also true that there are so many interests that you can imagine that to us kind of looked a little unrealistic, the idea that we could tell Meta or Google, oh, you know, you should put a data center there rather than here. And it's more a matter of understanding, given the situation, assuming that these events are random, we cannot control this source of randomness, what can we do? And what popped in our mind is, okay, we have entire field of research that are focused on power grid optimization, and most of them, though, are divided in two big groups. One is three, maybe. One is I want to optimize the grid to reduce emission. So this is power grid optimization for climate mitigation. Another point is I want to optimize the grid to reduce energy inefficiencies. And this is another approach. Some of them put things together. Some other works are focused more on the economic side. So how can I optimize the pricing of the power grid to maybe minimize both energy inefficiency and maximize the market. But no one of them ever took into account explicitly what are the health impact of certain allocation strategies rather than other. So our whole point here is we would like to minimize the adverse health outcomes as our metric for grid optimization. under, of course, energy and emission constraints. And here I provide you with some example of why makes the difference. In particular, this is a grid world. In this grid world, you have a population, then you have three different kinds of power plants of energy resources. Actually, dirty ones that are the red, then you have hybrid power plants, and then you have energy from renewable sources. And each one of these, based on their nature, will produce more or less CO2 and will produce more or less hazardous air pollutants. The point is that when you produce hazardous air pollutants like PM2.5, they are transported by the wind, so they can move around in the land. And here, I give you fixed a certain energy demand. I give you an overview of what would happen to the allocation if we first aim to just minimize emission. In the second case, if we just minimize adverse outcomes. And in the third case, if we minimize adverse outcomes by constraining the emissions. So here we are minimizing emissions. So what the model will do is that, okay, I will not use the dirty power plant. I will just use the hybrid and the renewable sources to meet the energy demand. But because of the wind in this grid world, the PM2.5 produced by the hybrid source will reach populated area. So you are actually minimizing emission, but the adverse set outcomes here, I just, of course, a number, it's 100, the emission is 200. So you are minimizing the emission, but you are not actually avoiding adverse set outcomes. In the second case, if we want to minimize adverse set outcomes, what you do is, I don't care about the kind of power plant that I use. I just care about where the wind is going, to put it very simply. Of course, it's not that simple, but so what this allocation will do is saying, okay, I don't allocate the hybrid one, but rather I allocate the 31 because the wind is such that it will not reach any populated area. So in this case, you are minimizing the adverse health outcomes, but you are not taking into control the emission. So this is purely short-term climate adaptation. This is purely long-term climate mitigation. There has to be a trade-off between them. And in this case, this is what you obtain with an allocation strategy that takes into account that wants to constrain the emission, but whose objective is to minimize adverse health outcomes. And what this allocation will do in this scenario is I use a little bit of everyone, and in a measure for which I can reach a reasonable level of emission that is very close to 200 here, but also I reach a very reasonable low level of adverse health outcomes that is very close to the level here. So this is kind of the idea that we have when we talk about health-informed power grid optimization. Now, I will not go into detail, but just to put there some math of why we are thinking to do this stuff. Because the first question is, what are you going to optimize? What are you going to allocate for the power grid? An example is the fuel mix of the region. So if you have, assume it's a sub-region of the US, in reality, those are the balance authorities that actually handle the grid. But assume you have a sub-region in the US, then to each sub-region, usually what happens is that a fuel mix is assigned. And the fuel mix is the fraction of each type of power plant that should be used to meet the energy demand. So 50% from renewable, 20% for dirty, 30% from hybrid. So this can be modeled easily as a vector in which all the entries are between 0 and 1, and of course they have to sum up to 1 because it's a percentage. So if we want to optimize this, we need to understand what are the source of randomness that we cannot take into control. This is the motivating point of my part of this part of the talk. First, what we cannot control in a pessimistic scenario? The total energy demand at a certain time. Then we cannot control what are the available supplies at a certain time for the different fuel type, because you will need to influence market at that point. And what you can control are the weather conditions, so how the pollutants will be taken around. So these are three sources of randomness for which we don't have a distribution. We don't know how to control. We just need to deal with that without knowing their statistics most of the time. And what are our quantity of interest? What we would like to minimize are CO2 emissions, hazardous air pollutants emissions, the energy availability, of course, given the supplies, a certain power plant can produce a certain percentage of energy. And then especially you cannot see it, but it's the number of hospitalization, is the health impact of this stuff. Like given a certain snapshot in which the fuel mix is allocated to some region in a certain way, what's the health impact of that? So, you know, I will go fast on this, but this is the type of very ugly problems that one will find themselves to solve in a setting like this. What you want to do is minimizing the fuel mix, minimizing with respect to the fuel mix, what? The long-term average number of adverse health outcomes. And of course, all of these functions that I here just put as function of time are in reality coupled among them. I'm not writing down explicitly how are they coupled. It depends on the model, and on the quantities they are considering. But we want to minimize the long-term expected average of the number of adverse health outcome, subject to the fact that long-term expected average of the CO2 is under a certain threshold. The long-term expected average of the hazardous waste pollution is under a certain threshold. And these are long-term objective function, long-term constraints, and instantaneous constraints. So the way you allocate stuff per each time step has to be such that the entries of the fuel mix are between 0 and 1. The available, so the supplies are enough to allocate a certain portion of the fuel mix to a certain power plant type. They have to sum up to 1 because these are percentages. They have to sum up to 1. So this is the kind of problem. I will not tell you how to solve it because there is not a single solution. The problem here is that you don't know how to compute that expected value in 95% of the time. So you don't know the statistic of this stuff. And there are two solutions for this. One is more of an hybrid model-based data-driven approach that could use like Q-theory, Lyapunov optimization, stabilization of complex systems. And this is an hybrid approach. And I like it more, going back to the fact that I am an hater of AI in reality. Or the second approach is using reinforcement learning. You don't know the statistical this stuff. If you have enough data, you can apply reinforcement learning algorithm to solve this kind of problem. In reality, you need a lot of data to solve this kind of problem with reinforcement learning, but that's another story. So this is our idea, or this is a possible instance of our more general paradigm of Earth-based power grid optimization. We don't want this to be the only instance. Okay. Fair. So this is just a possible instance, optimizing with respect to the fuel mix. But in reality, our paradigm can have different instances. We are currently working on it. And this was what I wanted to tell you about resilience to AI. So a possible element that we should design is how to be resilient to AI is to better understand how we allocate, we optimize the power grid. And of course, folks, and I don't know if any of you works on power grid optimization, that's an hard problem for several reasons. You need good models from the dispersion model, you need good models for the market, you need good models for several stuff. And especially you need to have practitioners that are available to move towards a different paradigms like this. And it does not always meet the expectation of providers that are more interested in profit rather than this kind of consideration. So there is also an advocacy work to kind of make these approach valuables. Let's move to the second part, that is, what can we use AI for in climate adaptation? The title is, I think, it's pretty exhaustive. What we want to do is a foundation model that is joint for climate and health. So fill the gap that I was talking about at the beginning. And this is just an overview of what people have done in climate. Here I focus on weather forecasting, but there are also more general geospatial foundation models. With the advent of AI. Before AI, what we had was physics-based simulation. So we had physical model that were forecasting weather for us. They are standard, they are strong. That's a good thing. But of course, with every model-based approach, if the model is not the right one, you will end up having biases and model mismatches. So you will have difficulties in this case to capture small-scale features or extreme events. And most importantly, these models that are strongly model-based have scarce data assimilation exploitation. So if I have a lot of data, it's harder to feed the data to them rather than to something else that is purely data-driven. And this is what people have been using AI for. The AI models are not always, most of the time, they are not physics-based for weather forecasting, but they've shown to be better accuracy. They are more efficient because we know how to use GPUs nowadays, so they are very fast. And anyway, we need to understand that these models come still with many limitations. In reality, what happens is that these models are usually used at the same time with physics-based model, but some of them have proven to be extremely good. This is just to give you some hint on the current landscape. This is the GraphCast model. I don't know if any of you ever read this paper. It's from Google DeepMind. And fun fact, I had the opportunity to talk with the project manager of this model. It made me laugh because each data point of this model per each time step is something around 20 gigabytes. Each time step, we are talking about years and years across the whole Earth surface. So, not exactly the kind of model that everyone of us could train at home, but the key characteristic of this model are the following one. They don't treat Earth as a grid. They rather treat Earth as a network plus a mesh. So what they use are graph neural networks to model this kind of stuff. There are graph-based model, deep learning model. And it's very nice because it's large scale and they can model long-range dependencies. So even if, the fake butterfly effect can be captured with this kind of model. The other approach is the Aurora model. This is a model from Microsoft, more recent, slightly more recent than GraphCast, but there's a very different approach. This is actually treats Earth as a grid, as a series of multi-resolution grids. So what they use are vision transformers to model this kind of stuff. From the ones of you that are more familiar with deep learning, probably you know what is a convolutional neural network. Vision transformer are the transformer counterpart of it. It's very fast, it's very scalable, can do the same thing that GraphCast was doing, but there is one major difference, that GraphCast is not a foundation model. This is a foundation model. The reason why this is a foundation model, like GPT, like Claude, like all the other, in philosophy, because it's not a language foundation model, it's just a foundation model, is the fact that these kind of objects are generalizable. In a foundation model, in 2 words now, it's hard for time constraint to explain it more in detail, but if we have time offline, I'm happy to talk. But you have to think about a foundation model as a very big model that is not trained in a supervised way, is trained in a self-supervised way. Think about it as a PCA on steroids. So what you get out of these models after the pre-training stage is a low-dimensional vector that is a very information-rich data summary. And the data that you can give in input to neural network, of course, can be multimodal, can be irregular. So the amount of data that these models can ingest are unprecedented. And now they are very good to extract information out of it and condense it in low-dimensional data. So what happens is you pre-train this kind of models on a vast amount of data, and you don't need labels to pre-train them. You have specific approaches. I will not go into detail, but trust me, you can do it. You don't need labels. So you could obtain those rich representations without using labels. And then the question is, okay, once I have this representation, what can I do with them? So GPT, what GPT does is when you input something, it creates an embedding of a sentence. So it creates an embedding of what you wrote, and then uses that embedding to solve the task at hand. That in the case of GPT is just complete the sentence. The way GPT replies to you in its mind is, I'm completing the sentence you are giving to me. But in reality, this is just to give you the sense. Before this stuff came out, we were not talking about AI. So when we talk about AI, we are 99% of the time talking about a foundation model. That's the algorithm behind the AI hype. Because you have a very good model that can extract a lot of information for the data. And what can you do with this information? You solve downstream tasks. So the same model can be used for multiple tasks with a very little additional training stage. For example, I don't know, I want to classify, I'll say some bullshit, but I want to classify the current time frame of the geospatial condition on Earth. I want to attach a label to it. What I do is I extract feature with the foundation model, I get this embedding, and then I pass that embedding as input feature to a linear regression or to a logistic regression. So it's a powerful way of extracting feature. It's more than that, but this is the main use. And the generalizability comes with the fact that those embeddings are information rich, are not task specific, so you can use them for a plethora of other tasks. And in this case of Aurora, for example, what you could do is that you can use the model to forecast weather at scales that the model hasn't seen. So they pre-train the model on a certain resolution. Then with very little data, you fine-tune, that's the terminology that it's used, you fine-tune the model, and the model can predict the weather at scales that it was not exposed to before. So that's the power of foundation model, and that's why we like it, and that's why GPT works, actually. And the same approach has been used in health for several different reasons, but the main motivation is the same in both cases. Weather, a lot of data without labels. Health, a lot of data without labels, because now we have massive EHR data and claims data. We have a lot of them, but we don't have label for it. And what was done before with just traditional ML or rule-based model has been replaced by foundation models. And this is very similar to text. I think it's more intuitive than weather, because EHR at the end of the day is just a bunch of text. So you can train a large language clinical model for doing this stuff. And this is what people have been doing in the last period in different ways. This is, for example, a model that comes from University of Florida. That's why Gator and NVIDIA. And this is a versatile architecture. What does it mean? This is actually a language model. What it does, the pre-training without the labels, the self-supervised, we ask the model to complete the sentence by masking part of the sentence. So you don't need labels for this. The sentence is there. And the model, by learning how to complete sentence, actually learns the semantics and the meaning of the sentence itself and is able to condense that in a very low-dimensional embedding. So what they did here is just, okay, University of Florida has a lot of data, the internet has a lot of data, let's feed it in a large language model. And this is generalizable, as can be fine-tunable for tasks. For example, they've used it for I've used the embedding at that point, the foundation model for rapid EHR annotation, for fraud detection, for clinical decision support. So here is a purely language-based approach, a lot of text fed to the model. But if you want, for example, to predict the trajectory, the health trajectory of a patient, what you will do is maybe putting time into the picture, and would the I don't know how to read it, but it's the BHRT model, that is a joke on the BERT style architecture, that was a model for Google. It's trained in the same way. It's still a foundation model. The only difference is that the time structure is injected in the model. So while for the previous model, they were just scattered EHR here and there, for this kind of model, they are ordered. So we are presented the health trajectory of the patient. We presented the health trajectory to the patient in order, with a time embedding and some other stuff that helps the model understanding how the temporal pattern goes. And of course, this can be used for different tasks, because you could do disease trajectory. You want to predict when the patient will be back. Or you want to identify high-risk patient for chronic condition based on their pattern in their trajectory. And it's a very interesting approach. But still, this is, again, more or less language-based. And this is, again, solely health. So we have all of these good models, Aurora, GraphCast, Gator, Trombert, and I've just named probably 4 out of thousands. No, thousands not, but hundreds for sure. And the point is, no one of these models is useful for climate adaptation, because the weather one don't have information about health, the health one don't have information about climate and socioeconomic variables. So let's do something that takes all of these into account and in a principled way to define climate adaptation strategies. And there is only one paper from Google that tries to do that. but unfortunately it doesn't work with time-varying data, so it's just a fixed time frame that, of course, it's kind of useless. But what we want is a model that is able to produce embeddings, the representation I talked about before, that this time have information about health outcomes, climate stressors, and confounder and socioeconomic variables. So about all of them at the same time. And what we want to do is the first climate and health foundation model. Because we have a lot of data, we have a lot of health data, we have a lot of weather data, we have a lot of socioeconomic data, and we have the expertise in our lab about climate adaptation. But the main goal for this is, the question is always that one, just to think with you in terms of the terminology. What are the downstream tasks? Once we have this big model that produces these very information-rich embeddings, what can we use them for in a context of climate adaptation? And in general, there are many different answers to this. I'll go in order. The first one is that if you don't adopt this kind of approach, it will be way more involved to use that amount of data all together, and to link them all together. That's the first. The second point is the importance of open source, the importance of sharing the embedding. When you want to use GPT on your laptop, what GPT provides you with are the embedding, because then you can use those embedding to your little models if you do research on the stuff. This will be the same. Like you have a huge series of confounder treatments, health outcomes. Can we provide you with the health outcomes? No, the data are private. Can we provide with all the rest together? No, because it's a lot of stuff, and you have your computer, maybe your limited resource. But what can we provide you is the embedding. We already performed a PCA on steroids for you. There is a lot of information in this vector. You can use it for your research. And for example, for the one of you that maybe are more in biostat and causal inference, you could use the embedding as confounders in a causal inference pipeline, in a classical causal inference pipeline. You can adjust for them, because there is a lot of information that will clean out a lot of noise from your task. And so ideally, what we want to do is doing this, show different tasks, maintain it, and eventually distribute the embeddings to the community. How are we going to do it? I will not go into details, but you have different technical obstacles here, because you have dependency. You have spatiotemporal dependencies that are short and long range, and these spatiotemporal dependencies are not only intramodality, so among outcomes, among treatment, among confounders, but also intermodality. So what you are interested into is also to check what are the relationship between outcomes and confounders, what are the relation between outcomes and treatment. So you need to take all of these in consideration. And the way we're going to train it is by stratifying the data, because if you want to use that for causal inference, you want stratification, you want complex stratification, actually. We are going to use a lot of ICD codes. I have an estimate for it. I think that we are going to train on probably around 100 ICD code for a first release of the model, and ICD codes that are trimmed to the third digit. So you're actually pretty high in the hierarchy, and you are capturing a lot of ICD codes that are currently assigned when you go for a medical visit. And the most important thing is this one. I don't want to talk about causal, like AI is not causal yet. AI will not tell you why things are happening, will not tell you with enough confidence. But what we can do is kind of bias the pre-training stage towards something that is eventually going to be used for causal inference. And because at the end of the day, when we talk about climate adaptation, what we really want is that those embeddings are useful to predict exposure response curve, this kind of quantity, because that's telling you if I change something, in which point of the curve am I? So it allows the model to answer some what-if-like or counterfactual questions. And again, what we're gonna provide a true evaluation of the model, because this is a very tricky point, but are not the embeddings to be causal themselves, are the embeddings that have been extracted in such a way they are ready for causal inference. This is a very important point, and I can elaborate more. But the way you force this is using two different approaches, and we will probably use both of them. The first one is having branches in the model, different branches. So for example, if you have confounded treatments and you want to estimate a propensity score, you will be able to, you would like to have a branch of the model that is able to predict the treatment from the confounder. And that branch of the model should not mix up with the outcome. So there are many tricks that one can implement to have this kind of guarantees. Not guarantees, but at least empirical guarantees. And also there are specific loss and pre-training approach that allow you to keep it more in a causal inference flavor. But yeah, so this is one of my last slides, and this is to wrap up because I'm sure that most of you, especially coming from biostatistics, are still asking themselves, okay, but why do we need this stuff with respect to what we already do? I think that the point is what I said before, is generalizability of stuff. When you do a causal inference study, what you do is, I have my target population, I have my target outcomes, I have my confounder and my treatment, I run my model here, I will give some results on this model, but if I change my population, if I change my outcome, or if I change my confounder, I have to redo it. So you have very rigid assumptions that, of course, come with a lot of very good stuff. For example, you have more interpretability. You know exactly a model, why it's doing something or why it's giving you some conclusion. The foundation model has a completely different philosophy, as I told you. Like, the generalizability is at its core. Like, the representation, if I pre-train the model, then I have new data. If I pre-train the model on the Medicare data set in the US, and then Macron comes here and say, okay, I want to use my data in the model. You probably, if you do things right, you need just a little fine-tuning, or you can just feed the data to your model, and the model will be able to extract the semantic information out of it. So you will still be able to extract embeddings across population, across outcomes, by using the relation between multiple outcomes, multiple confounder, and multiple treatments. And these are all stuff that if you want to do them directly in a pure causal inference pipeline, you will struggle with all of this stuff together. And then, again, we want to share embeddings. So we want to provide embeddings. And then what can we do with it? Some downstream tasks. As I told you before, the core of all of these, of all the foundation model is, what are the downstream tasks? What are you going to use those embeddings for? And all of these tasks, I want you to notice that statistically are usually pretty hard because require auto distribution or some generalizability capability of the model. For example, what if we pre-train the model on the East Coast and we want to, or what if we pre-train the model on randomly sampled location and we want to impute the others? A foundation model can do that. Or even harder, what if we don't do extrapolation? What if we pre-train the model on the East Coast and we want to obtain the results from the West Coast, for example, the prediction of an outcome on the West Coast without retraining? You can just feed the model. And then most importantly, can we impute exposure response curve in a more or less reliable way? Like, are the embedding enough information rich to have this kind of information in them? So this is just an overview. You can do more stuff, but I hope the goal here is that I wanted to convince you that foundation model could be useful for climate adaptation. Again, foundation model plus causal inference, foundation model plus causal inference plus humans in the loop. This kind of pipeline can make this object work. I mean, it's not magic, but yeah, this is what we are doing. And hope you liked. If you are interested in this kind of stuff, both of the resilience to AI or AI for resilience, these are my contact. And yeah, thank you for coming. Yes. That's kind of a fair point. No, we are in the process of doing it. We are, in this moment, almost done with the architecture. I should be able to start with the pre-training in a couple of weeks from now. So we expect to have, the pre-training should not take long, probably a matter of days, and then we expect to work on the downstream tasks. So probably by the end of the summer, we will have the workout. we want to make sure that our goal is for sure to foster research in our lab, but that's just a minimal part of it. And the second one, we need to make sure that we can distribute the embeddings. And actually, it's pretty tricky because the CMS data that we are using are, if someone you worked with them, you need to make sure people could always reverse engineer this stuff. But I hope, and I'm pretty sure that we will find a way with some differential privacy plus the fact that they are embeddings to release this kind of vectors. Yeah.
That formulation for the health impact of data centers that you had formulated the problem and then you said using reinforcement that
To me, it's not my favorite way of solving it, but it's possible. Yeah, the way we are currently writing down the algorithm is not through reinforcement learning. I use stochastic optimization, yeah, mostly. Like something more on the dynamic programming or Lyapunov side of thing. Because, it is true that you don't know the statistics, but at the end, you want a policy that allows you to have results on average in the long term. So even if you don't have the statistic, you can use some dynamic programming or Lyapunov base by just making assumption of what is, for example, the slope of the hospitalization with respect to pollution. But you know that it's almost monotonic in that case. So even if you use a surrogate, a line as a surrogate, the results are kind of good anyway.
Model for this, for example, for the energy consumption or for the weather forecast, also they are like have randomness, but still maybe you can fit a model.
Oh, definitely. I mean, the way, of course, everything we are talking about is on a simulation level because this kind of model are useful to validate the allocation strategy. And yes, the short answer is yes. For example, for the weather models, we could use Aurora to have prediction and run the algorithm on top of that because we know it works very well. And we are currently working with some people from engineering here at Harvard that worked a lot on the energy market side. No, it's Leshy. He just arrived, but I also know him, of course, because we want the more accurate is also the market model behind it. That the grid model, of course, is better. But everything must be on a simulated level, and this is always true every time you want to propose allocation strategy or perspective studies. I mean, otherwise, we should implement the allocation, but that's kind of the next step. It's the hard one. Yeah.
Yeah. I caught at least a couple of downstream causal inference tasks that I think you mentioned with the foundation model. I'm having a hard time reconciling these. So one thing that you mentioned was you could take the embeddings and like throw them in whatever or whatever else. So in that case, like I have a treatment that I'm interested in for an exposure, and I have an outcome that I'm interested in, and I want to use the embeddings as like But in that case, the treatment of those confounders can't be part of the embedding already.
Could be part of the embedding. It depends. At that point, you can use the model and leave the treatment out, for example. Like the foundation model. Something that maybe I missed, that all the confounders, and that's another cool thing, is actually you don't have to have a finite dictionary of confounder or treatment or whatever. Like if you have a new treatment, you can feed it in the model. If you don't want to feed that treatment in the model because you want to have an embedding that has not information about it, and you want to use it as confounder, you leave it out. And the model will, and also, yeah, that's a fair question as well, because the model, I made things simple, but in reality, what we are planning to do is to release not a single embedding, but a series of embedding that have more and more intricate dependencies among the element. For example, you will be able to access an embedding that is just an embedding of confounders, an embedding that is just an embedding of treatment, an embedding that is a now in machine learning, people say cross-attention, but an embedding that contains information of both. And eventually, if you are just interested in machine learning or supervised task, not in causal inference, we will provide also an embedding that has information about everything. Yes.
Some parts of the embedding don't overlap.
Exactly.
It doesn't have.
No, it doesn't have to be. It depends. And that's exactly what the model does. Like in reality, the what if question, of course, the exposure response curve is propensity score based. So in reality, what the model use to estimate them are just confounded treatment. There is no y there for sure. And then we use the outcome to write down the exposure response curve. But yes, and this falls into the, I think, the generalizability I was talking about. Like you don't have a finite list of things. Like if you come out with a new treatment or a new variable that should be a confounder or an outcome, you can just feed the model with it. The magic here relies on the fact that you had enough pre-training data to allow the model to extract information, meaningful information from it. This is more or less, to give you a very simple analogy, think about there are language models that are pre-trained in English and then are used to translate from, I don't know, from Italian without practically zero fine-tuning. This is more or less the same. Please, please. Mm-hmm. And ICD-10, that's another problem, but both of them. Pollution data, that's a lot. No.
Approximately in the types of data that you have in your lab, where do you fit on the scale to something very small, not something that's actually?
I mean, actually, you imputed empirically one of the main metrics that are used to design foundation model as scaling laws. And there is actually a sort of ratio between computation budget and amount of data. And yes, what we are planning to have, you have to consider we have time series or more or less, I think we will pre-train on like 40 confounders, more or less 20 treatments and 100 outcomes time series that are daily for 20 years. And so we are not even close to that scale. So we are not able to produce a model that is that big. This will result in having a foundation model that is smaller. So to give you a sense, I think that GPT-4o in this moment is 1 trillion parameters. That takes months to be pre-trained. I think will be in the order of hundreds of millions, this kind of model. That anyway, you can appreciate why classic statistical based is still, it's a small one though. Any other question? Go on.
So I in this formulation index is it's like the energy region.
Mm-hmm. Exactly.
The algorithm energy regions talk to each other because they like sell energy. So like that would seem to explode this problem quite a lot.
Yes. Yes and no. In the sense, the problem is, to me, they talk for sure. To me, it's understanding how often they talk and how dense is the connectivity there, but it's not super dense. Anyway, it all relies on, I mean, what you're saying, to me, it could translate in the fact that, for example, these HI are not independent, so this HI could be the output of a graph-based model, for example, or of a grid-based model if things are more regular, but in reality they are not. So I would say no, it's not a problem. Still, we are far below the amount of computation that you will need for the foundation model. Anyway, if we use reinforcement learning, maybe less. But if you use like Lyapunov-based approach, it's very cheap. Because at the end of the day, I can spoiler what's happened. What will happen is that if you use Lyapunov-based approach, that come with some assumption that we can make this kind of problem respect actually, but it's about time lags and stuff, is that you will practically minimize this problem without limits and expected value per each time. So that's the kind of optimization problem that you will end up minimizing. Per each time, you just forget about limits, you forget about expected values, you minimize the problem, you update some stochastic Q, and you have guarantees that it will converge to the same solution of this problem. So you have instantaneous problems that in reality are very cheap. Okay.
So that's thanks, Claudio, again.
Thank you. Yay. Thank you. Thank you for coming. Thank you.